I'm Harrison Clement,
I'm Parker Stenersen.
and together we are Deadwater Engineering presenting for the Carroll College Student Undergraduate Research Festival. This project coincides with our senior design course and seeks to design a pump and pipeline system for fluid transportation at a mine site in Montana. This project contains elements of hydraulic, environmental, and geotechnical engineering, as well as project management and drafting.
For this site, we were given available data and some data that we gathered. The available data given was a topographic map of the site location from our sponsor, Adam Jordanius, from Hydrometrics. He gave us a topographic map that contained a storage tank and the sizing of the storage tank, the pump house, and the location of the utilities and where everything else is at. Additional data that we gathered from him was the location in which we could use for this site. Granted that the client wanted to keep it closed for the public. So we estimated around Billings, Montana for a lot of our climate data. Additionally, we received a geotechnical report on the sand and on the layers of whether it was clay, sand, or what type of soil we were dealing with. Next is just a view of kind of the topographic map that we were given. And then the geotechnical report, in which we didn't have to use too much information from this. Next we dealt with was our design criteria, which we used a lot of it from Montana DEQ Circular 1, Chapter 6, dealing with moving contaminated water from mine sites. Much of our stuff came first was the storage tank and the elevation at 240 feet, which we dealt with, and we dealt with an 8-inch float valve and piping material. Next, we had to work with our pipeline, in which we had to use 3,000 feet of a material that was corrosive resistant, and it had to have check valves on it with backflow preventers from the storage reservoir backflowing into our pump. Additionally, we had to deal with our following criteria of the connections, in which everything had to be solid and excavated to a certain depth from our analysis that we have taken on this project. Lastly, we had to design our pipeline and a pump house, in which we had to have surge relief valves, shutoff valves on both sides, and a flow rate meter and pressure gauge to make sure flow is actually working and going through our pump. The last thing kind of in the design criteria that we had to work with was just going from the pump house to the storage tank, in which we had to have check valves stationed at 1,000, 2,000, 3,000 feet due to the long nature of our pipeline. Then we had to deal with constraints. The biggest constraints that we were able to that came up within our project was we had to have 2 pumps immediately readily available in case one pump failed, and that it could handle the amount of flow that we were dealing with the 200 to 550 gallons per minute. Additionally, the pumps had to be, and pipeline had to be corrosive resistant, and so we had to use a chemical process pump. Then we had to worry about the utilities. With the pump being placed next to a road, there were lines that power lines and vaults that we had to worry about underneath, in which we didn't want to delay construction processes further.
So initially we came up with 3 alternatives for our pump and 2 alternatives for our pipe. Our 3 alternatives for pumps all met the requirements of the project, and they were all within the scope of the work. And from there, it was just a matter of selecting which pump was the best for us. And the same goes for the pipe. Both high density polyethylene pipe and polyvinyl chloride pipe would meet the requirements of this project. However, you will see some pros and cons to both of those. And so for each of these alternatives, the cost evaluation was done, and most notably in the bottom graph here, bottom chart, you're going to notice the matrix of costs depending on the chosen alternatives. So strictly based on cost, our best alternative was to use a Gould's pump and HDPE pipe.
So once we kind of figured out all our preliminary designs and what constraints and everything we had to deal with, we went into a technical evaluation, which we only had to really use one major equation, in which it was the Hazen-Williams friction equation for total head loss, in which this was equivalent for finding out what we needed to get sizing wise on our pump to deliver the water from an elevation at 245 feet to elevation at 280 feet. And we designed this to go at 550 gallons per minute, just at a max rate, because then we would use a stop valve. So then that way our pump wasn't consistently running and would save wear and tear on our pump, because then it would allow time for the storage tank to fill up and not have to be in constant use of the pump. What we designed for, just due to the nature of the pump and pipeline, was an 8-inch sizing in diameter, which this allowed for us to have the least amount of head loss that we wanted and fit the design criteria within going from the storage tank to the pumping house, and then from the pumping house all the way up to the storage reservoir. And this is pretty much, this are results from that.
So here you're going to see a final cost estimate from our recommended alternative. This goes through all the different valves that are needed in this pipeline, most of them required by the DEQ circular. In addition, you're also going to see construction costs and the contingency of 15% added onto the end for any unknowns. Also, the Gould's Model 3296 Easy Mag pump was chosen here. We are going to be using 2 of these for redundancy, as mentioned earlier, and they are sized properly to handle the flow rates and pressures that we seek to achieve. For this project, we had to deal with some environmental and societal impacts, primarily dealing with hard metals in the water. And from this, we are not allowed to have any leakage occurring in the pipe or the pump systems. In addition, the high concentration of sulfate in the water is difficult on our equipment, and it must be able to resist buildup and also have the ability to remove buildup when that does occur. There were also some pipe protection areas implemented within the pipeline system, and these are checkpoints to look for possible damage in the pipeline and assess the life of the pipeline.
Presented here now is just our proposed pipeline. We wanted to give everyone an aerial view or a plan view of what the pipeline would look, following from the storage tank facility, the pump house, all the way up to the storage pond. We have a really big storage pond, so really that wasn't a problem at all. The hardest part, as you can see when we were designing, was having to designing the pipeline right along the road, and watching out for the utilities such as a power line, and then the mining roads in which we tried to go across with our correct distances. Furthermore, looking at the stationing, you can see how we have the checked valves stationed every 1,000 feet from our pipeline. A little bit more in-depth view, we gave plan views of where our storage tank, our pump houses are at, and what was within the storage tank and pump house. Due to the nature of being Carroll College students, we did not have the tools really available to us for throwing 2 and 3D models to design and display for, say, a contractor correct plan design views. But we worked with what we had, and that is demonstrated here. Additionally, what we have here finally is just an elevation view seeing how the depths of our pipe line and where our pumps are located at above and below ground level. The biggest concern for us was trying to decide too, along with the frost level. We had a concrete duct bank that was in our way, that which we had to make sure that the pipeline was deep enough below. So then that way we could get our pipeline going underneath, staying at a constant grade, making it easier for our pumps to handle. Thus, we set the base of our trench for the pipeline to be about 5 feet below ground level.
And so finally, here are some references, special notice to our project sponsor, Adam Jardinay at Hydrometrics, and our faculty advisor for senior design, Gary Fisher. Thank you.